A deep dive into sklearn, decomposition, dictlearning unraveling sparse representations. The dictlearning function in scikit-learn's decomposition module offers a powerful tool for finding sparse representations of data. It performs dictionary learning, a technique that decomposes a dataset into a set of basis vectors, the dictionary, and a sparse representation of each data point in terms of these basis vectors. This allows for efficient compression and representation of data, often revealing underlying patterns and structures. Let's dissect the key aspects of dictlearning. 1. The underlying principle: sparsity and dictionary learning. Sparse representation. The core idea is to find a minimal set of basis vectors, the dictionary, that can reconstruct the original data with a sparse combination of these vectors. This means that each data point can be represented as a linear combination of only a few dictionary elements. Dictionary learning. The goal is to learn this dictionary from the data itself. The dictlearning algorithm iteratively updates both the dictionary and the sparse codes until a desired reconstruction error is achieved. 2. The algorithm optimization problem. The learning process involves solving a challenging optimization problem. It aims to minimize a loss function that measures the difference between the original data and its reconstruction from the dictionary and sparse codes. Alternating minimization. The algorithm alternates between updating the dictionary given the sparse codes and updating the sparse codes given the dictionary. This process is repeated until convergence, typically using techniques like the coordinate descent algorithm. 3. Key parameters and their influence. N components. Int defines the number of atoms basis vectors in the dictionary. Choosing an appropriate number is crucial. Too few atoms might lead to insufficient representation, while too many can lead to overfitting. Alpha float regularization parameter that controls the sparsity of the sparse codes. Higher alpha values promote sparser representations. Fit algorithm. str. The algorithm used to learn the dictionary in sparse codes. Options include La's least angle regression and CD coordinate descent. Maxiter. Int maximum number of iterations for the learning process. Toll float tolerance parameter that determines the convergence criterion. 4. Applications. Image compression. Dictionary learning can effectively represent images with fewer coefficients, leading to compressed representations. Feature extraction. By identifying relevant features in the data, dictionary learning can be used for dimensionality reduction and feature selection. Anomaly detection. Outliers or anomalies may not be well represented by the learned dictionary, allowing for their identification. Signal processing. Dictionary learning is valuable in processing signals with sparse representations, like audio or biological signals. 5. Example usage. Python. From sklearn, decomposition. Import dictlearning. From sklearn, datasets. Import low digits. Import matplotlib, pyplot as plt. Load the digits dataset. Digits low digits, x digits, data. Perform dictionary learning. N components 15. Dictionary. Code dictlearning. N components. Reconstruct the data. Reconstructed data. Dictionary code. Visualize the dictionary. PLT. Figure fig size 10. 5. For I in Rangan components. PLT. Subplot 3. 5. I1. PLT. I am show dictionary. I. Reshape 8. 8. C map gray. PLT. Access off. PLT. Show. This code snippet demonstrates how to apply dictionary learning to the MNIST digits dataset. Learn a dictionary with 15 atoms, and visualize the learned dictionary. 6. Limitations and considerations. Computational complexity. Dictionary learning can be computationally demanding. especially for large datasets and high-dimensional data. Tuning parameters, finding optimal hyperparameter settings like N components. Alpha often requires experimentation and cross-validation. Interpretability, while dictionary learning can reveal underlying structures, interpreting the learned dictionary elements may not always be straightforward. 7. Alternative approaches. Principal component analysis (PCA). PCA provides a linear transformation to find principal components that capture the most variance in the data. It doesn't directly aim for sparse representations. Non-negative matrix factorization (NMF). NMF learns a dictionary with non-negative elements, often useful for representing data with positive values. Sparse coding focuses on finding sparse representations of data given a fixed dictionary. In conclusion, dict-learning in scikit-learn offers a powerful tool for extracting sparse representations of data. It can be applied to various domains for data compression, feature extraction, and uncovering hidden patterns. Understanding the principles, parameters, and limitations of dictionary learning empowers you to effectively utilize this technique in your data analysis workflows.